in the explicit finite difference method, you're actually doing something very similar, but it's a little simpler, however, than the implicit finite difference method. However, the explicit finite difference method may not give you a guaranteed convergence. So let's take a look at why, and in what situation that the convergence may be an issue. So if you set the finite difference method, if you set the partial derivatives like this, so this is still, so the partial derivative for t is fij minus f I minus 1j divided by delta t. So it's ij minus the one that is to the left of it divided by delta t. In the implicit is the one to the right minus this point divided by delta t. So if you look at the grid, say for this point, the partial derivative of df dt in the explicit calculation is really the f value here minus the f value here divided by delta t. In the implicit is f value of here minus the f value of here divided by delta t for the partial derivatives that we can use here, okay? So the explicit it is minus the one to the left. Now, if we do that, and essentially this is at the same, then it just made this substitution, and then you plug that into the formula again, and rearrange. So again, you pull out those ones that related to fij minus 1, fij, fij plus 1, and fi minus 1. So the same factors. Now here, you will see that you again have those things in the bracket, but there are different ones now compared to the implicit. You can then, let's give them some names. So instead of use AJ, we call them AJ star, BJ star, CJ star, okay? Now, you link, however, when you look at it, what do you link? You link Fij minus 1 and Fij and Fij plus 1. So they're all at I here with the Fi minus 1j, which is actually towards the left of those numbers. So graphically, what you have seen here is you're linking this point with 3 points to your right. For finite, for implicit, is you're linking 1 point here for 3 points here. But for explicit, you're linking 1 point here to 3 points here. That is 1 time step further. So if we look at this, it looks awfully similar to a trinomial tree, actually. And indeed, if you look at those AJ star, BJ stars, CJ stars, and look at those expressions, they're actually the probability of the star moving down, unchanged, or moving up. Okay, so now if they are in a way probabilities, then they must add up to 1. And if you have volatilities and those parameters in such a way that when you add them up, they don't get to 1, then your explicit finite difference method would not converge. So to ensure it converges, we have to make sure that each of this one, the AJ star, BJ star, and CJ star, each of them are positive, and you add them together, they come to 1. Now, so therefore, that since we know the boundary conditions, we for this 3 number we can determine this. For this 3 number we can determine this. For these 3 numbers we can determine that. So essentially, out of this equation here, we can determine every position here, every F value here, and you repeat that the same way you determine this. The explicit finite difference method is actually very easy because all you need to do is you are calculating a discounted expectation. Out of those ones, you get an discounted expectation here. And it's much easier to do than solving simultaneous equations. And you can do them, point by point, one at a time. And this is essentially, it's like a trinomial tree. Now, again, if you have a American option, you can calculate the expected discounted value. And if that value is less than the immediate exercise value, you'll replace the F value here with the immediate exercise value rather than the discounted expected value. Okay, so then you get a whole set of numbers here. And then you repeat that every time when your immediate exercise value is greater than the discounted expected value, that the immediate exercise value is the value you use here. And then eventually you calculate the F value along this line here. And let's say this one is the current stock price, and you will the F value calculated here is the option value that corresponds to the current stock price, and you get your option value. Okay, so with this, we conclude the numerical procedures we do for finance. And I will see you in the next lecture.